The molecular compounds that we saw in the last section were held together through shared bonding electrons. In that case, there was always some electron density deposited between both of the atoms in the bonding pair. This could happen because the atoms were all nonmetals and they were pretty close to each other on the periodic table, thus giving them relatively similar properties. Ionic compounds use a different model. They transfer electrons between a species that prefers to be negatively charged and a species that prefers to be positively charged. These oppositely charged pieces form an electrostatic attraction that keeps the pieces of the compound interacting with each other. Ionic compounds will involve a metal and either one or a group of nonmetals. This means that the whole periodic table is free game for forming our ionic compounds. Because we have more types of elements to work with here, we also end up with more rules. We'll have to first figure out what kind of pieces we have in our ionic compound, and then we'll name those individual pieces, and then we'll combine those individual names to name our entire compound. There's a lot for you to do here learning-wise. You have to spend a good amount of time on this section or you won't be able to master it. Make sure that you set aside enough time to practice often and practice well. This video will focus on monatomic ions or ions formed from the main group elements on the periodic table. These are commonly called type 1 ions because they can have one and only one type of charge. Transition metals, which we'll see in a later video, are commonly called type 2 ions and have a different set of naming rules. First, let's talk about those pieces that do and don't prefer to have electrons around them. When we talk about atoms, we're talking about species that are neutrally charged because there are the same number of protons and electrons present. Take fluorine, for instance. Since it has an atomic number of 9, an atom of fluorine will have 9 protons and 9 electrons. 9 positive and 9 negative things make a neutral compound overall. And we could do a similar thing with sodium, whose atomic number is 11. An atom of sodium will have 11 protons and 11 neutrons. Now, this electron count is all fine and good, but in reality, lots of times our atoms would rather be ions, or species that carry permanent charges. This is because those atoms prefer to have the same number of electrons as their nearest noble gas. This will become more clear when we discuss electron configurations in Module 5, so for now, know that you have to believe me that this is a true story. Having the same number of electrons as another species is called being isoelectronic with that species. In the case of fluorine and sodium, that nearest noble gas is neon, an atom which has 10 protons and 10 electrons. Note that neon is on the same row as fluorine, but it's on the row above sodium. The nearest noble gas is not always on the same row. It will be the noble gas whose atomic number is closest to the atomic number of the element that you're working with. Electron, it would have the same number of electrons as neon, or it would be isoelectronic with neon. This extra electron that is gained has a negative charge associated with it, so once fluorine gains this 10th electron, it now has a permanent negative charge equal to the charge on that electron. A species with a permanent negative charge is referred to as an anion. Fluoride, the ion formed from fluorine, is specifically referred to as a monatomic anion because a single atom of fluorine becomes a single fluoride anion. Anions behave differently than atoms do. Because of this, they have different symbolism and they get a different name. The symbolism is simply the symbol for the element plus the appropriate charge. Gaining one electron will give us one extra negative charge, thus the 1 minus. Charges with a magnitude of 1, whether positive or negative, will always have an implied number, much like the subscripts 1 in our chemical formulas. The charge will have to be present, but the number should not be present. In terms of the name fluoride, that should look familiar. Remember the chart of IDE endings in molecular nomenclature? There, they denoted the more electronegative element because it came second in the formula. So it should make some sense that we can reuse that table when naming anions, which also want electrons. Which brings up another great point to remember. We're able to double dip on that table because the majority of our non-metal elements are going to form anions. Not all, but most. There's more on this in just a bit. It would need to lose one single electron in order to be isoelectronic with its nearest noble gas. Losing one negatively charged electron would give a species with a permanent charge of 1 plus. Species with a permanent positive charge is called a cation. Sodium is specifically referred to as a monatomic cation because a single atom of sodium becomes the sodium cation. Again, cations will behave differently than atoms or anions, so they need their own notation and naming system. The notation will follow the same pattern that we saw with the anions, the elemental symbol followed by the appropriate charge as a superscript. The name is simpler than the anions. We simply add the word cation behind the elemental name, at least for sodium because it is a main group element. Our main group cations will lose the same number of electrons each and every time they form a cation, so there's never any variation here. Because of this, we only need one name for these cations. As we will see in a bit, you'll need some transition metal cations eventually, and you have to name these more specifically because there's variation in the charge there. To start with, because they gain and lose one single electron respectively to be isoelectronic with their nearest noble gas. But our atoms will do what they need to do in order to have the same number as that nearest noble gas, and that often means gaining or losing more than one electron. Oxygen precedes fluorine on the periodic table. Because oxygen has an atomic number of 8, an atom of oxygen will have 8 electrons. This means that that atom is trying to get to a total of 10 electrons. It will need to gain 2 electrons to do so, forming a 2- ion. Nitrogen, just to the left of oxygen on the periodic table, will need to gain 3 electrons to move from the 7 the atom has to the 10 electrons the ion wants. We can work beyond sodium as well. Magnesium would need to lose 2 electrons to move from the 12 to the 10 the ion wants, forming the magnesium ion with its 2 plus charge. Aluminum would need to lose 3 electrons and would form the 3 plus aluminum cation. All of the atoms given in these boxes have different numbers of electrons. All of the ions given in the text boxes below have the same number of electrons. So our different atoms are not isoelectronic with one another, but our different ions are isoelectronic with one another. Here, all of the ions end up with 10 total electrons, so they are all isoelectronic with neon. Some notes about our names and our notation. Notice that nothing name-wise is capitalized. Our elements, atoms, ions, molecules, and compounds are not proper nouns. If they aren't at the beginning of a sentence, they should be written in lowercase. Note also how the charge is included in the symbolism, which is shown larger here. How big the charge is goes first, and then the sign on that charge goes second. The chemist doesn't write O minus 2. You'll need to get out of that habit of doing so as well. The content page shows you what the balanced chemical equations for the loss or gain of electrons looks like. Be sure to review that so you can prepare similar equations if you're asked to come quiz time. We can use the periodic table to help us determine the charges on our monatomic main group ions. You're expected to know the common charges for the monatomic ions listed in this figure. If you prepare flashcards, it's going to help you remember these. Now, this is a really important idea. The next video in this subsection actually explains this again in more detail and in a slightly different way. So group 1 could either lose one single electron and have the same number as the noble gas on the row above it, or it could gain 7 to get to the same noble gas as its row. Now losing one is a lot less work, so that's what this atom is going to do when this atom forms an ion. All elements in this first column will form cations with a 1 plus charge. Group 2 could either lose 2 electrons or gain 6, and losing 2 is the easier play, so all of our alkali earth metals are going to form 2 plus cations. When we get over to group 3, we really just consider what aluminum will do when it forms an ion. We don't really work with those elements below aluminum very much in this course, though if you are asked questions about these, just use aluminum's rule. You cannot do that with boron though, as it tends to form covalently bonded molecules and not ions, so you won't really ever form a charged species for boron. At any rate, aluminum will lose 3 electrons and form a 3 plus cation. Notice that all of these columns work to lose electrons so that they can have the same number of electrons as the noble gas on the row above them. The anions, on the other hand, will work to become isoelectronic with the noble gas on the same row. As we've seen, fluorine will gain a single electron to become the 1 minus fluoride anion. All of the halogens below fluorine will do the same. Oxygen and the elements in its group will form 2 minus anions by gaining 2 electrons. Nitrogen and the elements in its group will form 3 minus anions by gaining 3 electrons. Now, technically, when we get to the carbon column, we could either gain or lose 4 electrons. I tend not to give you carbon and silicon because of this ambiguity. In reality, either losing or gaining 4 electrons would make a pretty unstable species, so it isn't all that likely that that will happen. Think of carbon as part of molecules and not something that will ever transfer electrons. Lastly, there's nothing under the noble gas column because those don't form ions. They just don't have to. Everything else is trying to get to what they already have, so they're not going to have to work for it. We've only gotten part of the way through naming our ions, but since there are a lot of compounds formed from monatomic ions, we can actually do quite a bit already. Now, as a review, ions are atoms or groups of atoms, which we will see in the next subsection, that carry a permanent positive or negative charge. If an atom gains one or more electrons, an anion forms. This anion will have a permanent negative charge. Our nonmetal elements form anions, and these are named using the same IDE endings that we saw when we saw molecular nomenclature. If an atom loses one or more electrons, a cation forms. This cation will have a permanent positive charge. All of our metal elements will form cations, though right now we have just focused on the main group elements. We simply add the word cation to the element name in order to name these species for these main group cations. You can use the periodic table to help you determine the charge on your monatomic cations and anions.